Hello everybody, welcome to another movie on differentiation. The examples for this movie is taken from Thomas's Calculus, chapter 3. We are specifically going to learn about the chain rule. So if you have not seen the previous video on differentiation, I would highly encourage you to go and watch that before you watch this movie. So chain rule is used when there is a function, when you have to differentiate a function within a function. For example, let me give you an example. Let's say we have a function y equals x squared. We know how to differentiate this. This is dy over dx. That's the derivative is equal to 2x. That's the derivative. So we know how to do that. But the chain rule is used when we ask to get the derivative or differentiate x squared plus 3 to the power squared. That's when you have to use a chain rule. I'll give you another example. If y is equal to sine x, the derivative is very easy. Dy over dx is cos x. But if the x is replaced by a function, that's when you need the chain rule. So let's take an example. If y is equal to sine, x is replaced by a function like 3x squared plus 2x plus 1. That's when you have to use a function within a, because it's a function within a function, you need to use the chain rule. Another example would be if y is equal to ex, we know the derivative is dy over dx is equal to ex. But if this x is replaced by a function of x, for example, y equals e to the power 3x plus 4, that's when you need to use the chain rule that we are going to learn today. Another example would be if y is equal to ln x, we know the derivative dy over dx is equal to 1 over x. But if we have a function of this nature, y equals ln, the x is replaced by a function of x. So that would be like, for example, it would be 3x plus 2. Then we have to use the chain rule to get the derivative. So here I've shown 4 examples, 1, 2, 3, 4 instances where we need the chain rule to find the derivative. So if it's a single function, you can find the derivative. But if it's a function within the function, that's when you need the chain rule. Let's have a look at some examples. So here we see a function within a function. So if it was y equals x squared, we know the derivative of that. Because this is a function, instead of a single x, we need to use a chain rule. So in the chain rule, what we do is we call this function something like u. So we say let u be equal to 3x squared plus 1. So if u is equal to that, we can write this, we'll separate it out. Then we can say y is equal to u squared. We substitute this there. And then we can say u is equal to 3x squared plus 1. Now we wrote the same function. We separated out the functions so that this would be a single function and this would be a single function. And here we are asked to find the derivative. So we are asked to find dy over dx. So dy over dx can be written as dy over du times du over dx. we can use that. So we keeping that in mind, let's do a derivative because this is just a single function and this is also a single function that you can get the derivative of. Let's use dy over du. So dy over du, we use this function, the way we derive that, it is 2u. That's the derivative of dy over du. Then here, if we do du over dx, we get 6x. That's 6x. Then we substitute this part and this part to get dy over dx again. So dy over dx is equal to, substituting this, 2u times, this is 6x. So we'll then also replace u by x. We know u is 2 times 3x squared plus 1 times 6x. So that's the answer. So all we did was we took this function and substituted, we called it u, and then we wrote the function as two functions, as y equals u squared and u equals 3x squared. Then since we've also find dy over dx, dy over dx can be written as dy over du and du over dx. So we differentiate dy over du as 2u, du over dx as 6x, and then we combine these from this, and that's what we get. Let's do this example next. We are asked to get the derivative of of cos t squared plus 1. So if y or xt was cos t, we know the answer. Cos t is minus sine t. But here, because there is a function instead of a single variable, we have to use the chain. So let's substitute. We'll take this as u. So let u be equal to t squared plus 1. Now we'll separate out the functions. So, and we'll call this y for simplicity. So y is equal to cos u, and u is equal to t squared plus 1. So then we get dy over du is equal to minus sine u, and du over dt is equal to 2t. That's when you differentiate this part. So since we were asked to find dy over dt, which is equal to, it can be written as dy over du times du over dt. And we know now that this is du over dt and dy over du is this value. So let's write that again. This is equal to minus sine u times du over dt is 2t. And we'll substitute the u here. So we get minus sine u is t squared plus 1 multiplied by 2t. We could also bring the 2t forward. So we can write this as minus 2t sine t squared plus 1. Let's do another example. So in this question we see that y is equal to sine x. squared plus ex, and we are asked to find the derivative with respect to x. So we are asked to find dy over dx. So let's write y equals sine x squared plus e to the power x. We know that derivative of y equals sine x. But the problem here is the x is replaced by a function of x. So dy over dx, we know it's cos x. So let's say let's use u as second function, x squared plus e to the power x, and we separate it out, so we know y is equal to sine u here, and then u is equal to x squared plus ex. So if we get dy over du, we see that is derivative of sine u is cos u. And du over dx is equal to 2x plus ex. Now we are asked to find dy over dx, so we know dy over dx can be written as dy over du times du over dx. So we see that du over dx is this, dy over du is here. So we have cos u times this 2x plus e to the power x. So we can replace u by this, and we can bring this part to the forefront. So we'll call it cos, and we are replacing this as x squared plus e to the power x and multiplied by 2x plus e to the power x. We can bring this to the forefront, and we can say it's 2x plus e to the power x and multiply that. We are rearranging to the terms only here. So it's cos x squared plus e to the power x. So that's the answer to this question. Let's look at another example. So the next example is y to the power e cos x. So we know if the function is e to the power x, we know that dy over dx is equal to the same function, e to the power x. But here we are asked to find e to the power cos x, where it is not a simple x, but it's a function of x. So we, to simplify, will take u as cos x. And then we say, we separate it out. So we know y is equal to e to the power u, and u is equal to cos x. So next what we are going to do is use one of the functions we did before, but instead of dividing it into a u function and differentiating it as two functions, let's try to do this as one function. So there's a straightforward way. So when you look at this, you feel like it's a function within a function. So it feels like it's a pregnant function. It's a function within a function. For example, this is the baby function. This is the baby function, t squared plus 1. And then we see there is a parent function. We'll have it in that includes the mother function, includes the baby function. So what we do here is, first we differentiate the mother function with the baby function and multiplied by the differentiation of the baby function. So let's start with first I will differentiate the mother function, which is cos t squared plus 1. So dy, this is equal to y equals xt, y over, sorry, we can say dx, we don't have to say y, dx over dt is equal to, so when we know d over dt of cos t is equal to minus sine t. So let's do, it's minus sine. Now instead of t, we write as we differentiate the mother function, which is cos, we keep the baby function as it is when you're differentiating the mother function. You do not separate the baby function out. And then you multiply it by the differentiation of the baby function, which is 2t. And we can bring the 2t out to the left, to the front. So we can say minus 2t sine t squared plus 1. So this is straightforward, and it doesn't have those multiple steps. And if you can learn this way, it will be faster and more productive. That's what I think. But I did the same thing as u, separating it out as u, and did it as two functions. That's the original way of doing it. That's from basic principles. But if you want to think of it as a mother function and a baby function, you can do that as well. So here, if you look at this, this is the mother function, differentiation of the mother function, while keeping the baby function the same. Remember, when you're differentiating the mother function, you do not do anything to the baby function. You keep the baby function, is not harmed. And then you differentiate and multiply it by differentiation of only the baby function, because mother has been already taken care of. Okay, so let's do another question with this a similar question. So let's say xt is equal to cos e to the power t plus t squared plus 1. So here the baby function is this, and the mother and the baby function is the outer shell. So let's first, we know the differentiation of the mother function. So we have minus sine. We keep the baby function as it is. We differentiate the mother function and keep the baby function as it is. T plus t squared plus 1, and then multiplied by the differentiation of the baby function only. So it is e to the power t plus 2t. And make sure we put the baby function in brackets, because that's how it should be. There are multiple values here. You put the baby function after you differentiate it. We protect it with two brackets. So let's keep doing it this way, because it's 1 or 2 lines and it's faster. So this is another function we did. So dy, we did this already by substituting this as u. So let's do this as mother and a baby function. So we have this as the baby function, and the mother function is the exterior with the 2. So we know how to differentiate y equals x squared. So then we'll do dy over dx is equal to 2x. So dy is, now we integrate first the mother, sorry, not integrate, differentiate first the mother function, which is 2 times the baby function. So it is 3x squared plus 1. We do not change the baby function. Now we multiply it by the differentiation of the baby function. So when you differentiate this part, you get 6x. That's all. So we can take this to the front. So we can write it as 12x times 3x squared plus 1. Okay. So we'll change the function a little bit and work on it. So if this is equal to cos x squared, let's use that. So dy over dx would be, we multiply this by, we differentiate the mother function. So it should be 2, you write the baby function, 2 minus 1 is 1, and then you differentiate the baby function, which is sine x minus sine x. You can take the minus out, so we get minus 2 sine x cos x. That's the differentiation of this function. So we can also do another example where y is equal to, let's say, cos x plus ex to the power 3 this time. So this is your, I'm only going to draw the baby function. So this is the baby function. So we'll just first differentiate the mother function. So it's 3, write the baby as it is, cos x plus e to the power x, and then we subtract 1 power from that, you get 2, and then multiply by the differentiation. We protect we put that in brackets. So cos x, when you differentiate cos x, you get minus sine x and plus e to the power x. So I'll rewrite it again on 1. It should be dy over dx. As soon as you differentiate, you should write it as dy over dx. So I didn't do that here. You have to, as soon as you differentiate, you write it as dy by dx. dy by dx is equal to, we'll take this to the front. We can say minus sine x plus e to the power x times, we keep the 3 here because that's the 3, and then we write cos x plus, there should be a bracket here, plus e to the power x squared, whole thing squared. Okay, let's do one more example. So let me do this as well. So dy over dx, we are differentiating this. First, let me rewrite this function. So we have y equals 1 over 3x minus 2, which is equal to 3x minus 2 to the power minus 1. Now dy over dx is equal to, now here the baby function is this, and the parent function or the mother function is this all together. So let's write, we'll differentiate the mother function. It's minus 1. We write the baby as it is 3x minus 2. We are using the power rule here, and we subtract 1 from here, so it's minus 2. Now we differentiate the baby function, which is 3. We'll take it to the front, so it's minus 3 and 3x minus 2 to the power minus 2. This could be also written as minus 3 in the numerator and 3x minus 2 squared in the denominator. Because of this minus sign, we can bring it to the denominator and make it a positive power. So here we see that y is equal to sine to the power 5x, and we see that the baby function here is sin x, and the parent function or the mother function is the entire thing. So dy over dx is equal to, integrate the differentiate the parent function, 5 sine, keep the baby function the same, and then multiply it by the baby function in differentiation of the baby function. So the differentiation of the baby function is cos x. So, and then remember this part is the mother function. So we do not, when we are differentiating the baby function, we do not use the 4 because the 4 was really the part of the mother function. So let me make that clear. So the baby function is this. Mother function was the entire thing including the 5. So it's very important that we separate those two functions out. So this is a very interesting function. So y is equal to, sorry about that, y is equal to e to the power square root of 3x plus 1. So here, this is your baby function, and the mother function is the entire thing. Now we do know how to differentiate e to the power x, because d over dx e to the power x is equal to e to the power x. So let's first differentiate the mother function. So dy over dx is equal to e to the power square root of 3x plus 1. Now we multiplied by the differentiation of the baby function. The baby function is 3x plus 1 to the power half. So that is, we multiply the power by half, and because the power is half, and then we write 3x plus 1, then it's half minus 1, and then we again multiplied by this function, differentiation of this function, 3x. So I don't know whether you saw it. It's function within a function, and it is a 3-tiered function. So let me explain that a bit further. Sorry, I think I made a mistake here. It should be 3, not 3x, because differentiation of this is 3. Here, the baby function had 2 layers. So this is the differentiation of the baby function, right? And the baby function had 2 functions as well. So first we differentiate, if you take the baby function, first we differentiate the 3x plus 1 to the power minus half, sorry, positive half. So what we do is we multiply this. Now this is the answer, okay? I'm recapping this. So this was the baby function. So you multiply it by half, 3x plus 1 minus half, because half minus 1, we have to subtract 1 because that's the power rule. And then you multiply the difference by the differentiation of this. So this becomes, though this is the baby function shown there, this is the baby function shown here, but it also has another baby function inside that. So let me put it in a light blue, there's another baby function inside that as well. So you have to differentiate that, which is 3. So this encapsulates what I did here. Okay, I think that was a very interesting problem. So let's do another problem similar to the one we did before. So let's assume the function is y equals sine square root of 3x plus 1. So this also can be written as sine 3x plus 1 to the power half. Okay, so here we do have a baby function, right? And within the baby function, there is a second baby function. And the overall parent function is this. So it's a 3-tiered function. So let's first differentiate dy over dx, the parent function, keeping the baby and the function inside that the same. So sine, we know a differentiation of sine x is equal to cos x. So we say cos 3x plus 1 to the power half. Now we differentiate the pink baby function. The pink baby function is half, this is times half, keeping the blue baby function the same, half, it goes to minus half. And then we multiply that by the inner light blue function, differentiation of the light blue function, which is 3. So we can bring 3.5 to the front, close to the equal sign. So we become 3 over 2 cos 3x plus 1 to the power half. And this can be brought to the denominator. When you switch from numerator to denominator, you lose this sign. So the sign can be positive. So it becomes 3x plus 1 positive half. Because we brought it to the denominator, from the numerator, we lost that half, and because this is the same. Let me keep doing 3-tiered functions. So let's do y equals ln, what do we say, x squared plus 2x plus 1 to the power 2. So here we have the mother function, which is the entire function, right? And mother function is the entire function. Mostly this is your mother function. And then we have the first baby function, which is with the 2. And the second baby function just within this. So the first function, omitting the 2 baby function, is L. So we know when y is equal to ln of x, it is dy over dx is 1 over x. So let's first get the derivative of the mother function. So ln of anything is 1 over x squared plus 2x plus 1 squared. I told you, as we do the derivative of the mother function, we keep everything else the same. So now we multiply that by the pink baby function. The pink baby function, when you differentiate, you get 2x, we keep the inner baby function the same, x plus 1. That's the outer function. Then we differentiate. I'll get rid of these. Then we differentiate the inner function. We multiply that by the inner function. So the inner function would be 2x, I will put brackets just so that we keep it separate, 2x plus 2. Now we can take this to the close to the to equal sign, and we can get rid of one of these, right? So we can say it is, we can take one of these 2's out with this, or we'll take 2 times 2 x plus 1 over x squared plus 2x plus 1. We can simplify this further. 4 times x plus 1, and we can factorize this, which would be x plus 1 squared, right? So we can cross off these. So we'll get 4 over x plus 1. One more question. Next, I will do exercise 3.6 from Thomas's calculus. I will do 10, 12, 14, 16, 18, 20, and 22. I would like you to do the same from 9 to 21, and I will include the answers for 9 to 21 at the end of the video. So let's quickly start working on 11 to 22, only the even number. So let's take 10, that is y equals 4 minus 3x to the power 9. So what we do here is, this is your baby function, and the outer layer would be the 9. So dy over dx is equal to 9 times 4 minus 3x to the power 8, and then you multiply that by the function, the derivative of the baby function, which is minus 3. 4x minus 3 would be minus 3. So we take the minus 3 out close to the equal sign. So we get minus 27. 4 minus 3x to the power 8. So we'll do 12 next. Y equals square root of x over 2 minus 1 to the power minus 10. So here dy over dx, let me first draw the baby function here. So that's the baby function. So we the differentiation of this would be 10. We keep the baby function as it is, over 2 minus 1, and we subtract 1 from this. That's the power rule. So we, sorry, it should be minus 10. So when you subtract 1, you get minus 11. Now we multiply by the differentiation of the baby function. So x over 2, square root of x over 2 is half times another half x to the power minus half. So let me do this separately. So when y is equal to square root of x, we can write it as y equals x to the power half, and dy over dx is equal to half x. Half minus 1 is minus half. So that is equal to 1 to root x. Okay, so that's what we can bring the, if you want, we can bring the 1 over 4 close to the equal sign. So we have minus 10 over 4 square root of x. We bring this to the bottom, multiplied by square root of x over 2 minus 1 to the power minus 11. So you can even even simplify it further, but I'll just keep it like and move on. Root of as it is as we differentiate the mother function. So minus 4x plus 6. Half minus 1 is minus half. Now we differentiate the baby function. Baby function 3x squared is 6x minus 4. So we can always bring this to the denominator. We can say we can bring a 2 from this because there's a factor of 2 common. So we say 2 out of 2 and then we bring this to the denominator. So it's 3x squared minus 4x plus 6 to the power half, and this is x minus 2. We can cross off the 2's and we can write it as y over dx. If you don't write it as dy over dx, it's seen to be equal to y. Okay. Pi minus 1 over x. We have to get some information about the derivative of cot. So I'll bring in some information. So this is some important information here. What cot x is. So cot x is cos over sine, just like dx is equal to secant squared. And let me first draw the baby function. This is 2. So I'll erase this so that we have enough space. So we take this minus close to the equal sign, and minus times minus we get plus, so we have 1 over x squared secant squared pi minus 1 over. Let's do 18 next. Let me write 18. 18 is y equals pi cos minus 4x. So this is your baby function here. This is your, sorry. So we multiply minus 4 by 5, that is minus 20. We keep cos as it is, and we subtract 1 from here, so we have minus 5. And when we differentiate the baby function, which is cos x, we get minus sine x. So we bring it to the front, it's 20 cos minus 5x times minus sine x. Let's do 20 next. Y equals e to the power 2x over 3. So this will be your baby function here. This would be your baby function. This would be the entire t of this would be the parent function that encapsulates the baby function. So this should be dy over dx because it's already differentiated, and we can keep this as equal because that reflects that it's the differentiation. So we must make sure we write dy over dx. So first we differentiate the parent function. E to the power x is always the same. So e to the power 2x over 3 multiplied by the differentiation of 2x over 3. Differentiation of 2x over 3 is just 2 over 3. So we'll bring the 2 over 3 close to the equation. So 3 e to the power 2x over 3. Let's do 22 on the other page. So here the baby function is this part. The parent function includes the baby function, and it's e to the power baby function. So let's do dy over dx is equal to, when you differentiate e to the powers, for example, if y is equal to e to the power x, dy over dx is equal to e to the power x. So the differentiation of the parent function is same as the differentiation of the of the function. So x plus x squared. Now it's time to multiply it by the differentiation of the baby function. So let's multiply it by the differentiation of the baby function. So it is, we encapsulate it with brackets. So we have 4 and it's x to the power half. So we divide it by half.